thank you. Yeah, I'm leaving tonight. So if you have any questions, please don't hesitate to ask. So, so we will today discuss these BCFW recursion relations. I hope at the end of the lecture, there will be few minutes left that I say something kind of more esoteric, or where the careful study of these recursion relations went in some new ideas about what the amplitude actually is as a single object. But let's get going here. So just a reminder, we have color-ordered amplitude for gluons in the Yang-Mills theory. We wrote it as a sum of traces multiplied by an ordered amplitude. Then we considered helicity amplitude, so with fixed external helicities. We introduced this new index k, which counted number of G minus, I would call it shortly like, negative helicity gluon. So together with that, for example, one object that we can consider is a 4-point amplitude. I would write A42 with 2 negative helicity gluons, 1 minus, 2 minus, 3 plus, 4 plus. So for example, this is the object we would like to calculate, and we will do it in the beginning of this lecture. Yeah, I said that some amplitudes are 0, so if the k is 0 or 1, the amplitude is 0, except one special case for k equals 1, that's the amplitude A31. That one is not 0. Yeah. And similarly, if k is n or n minus 1, the amplitude is again 0, except the 3-point. Yeah. Again, except A32, which is non-zero. These are the 3-point amplitudes we calculated before. Okay, then we had this long discussion about the Cauchy's theorem and the shifts and the factorizations. So the recursion relations that we constructed in the end, that was the final formula. Calculated the amplitude AN. Sometimes I will specify the index k in case it's important. We will do it once we do explicit calculation. But these formulas work for any k, so I can just also drop it. Yeah, so here it was a sum of the amplitude on the left. On the left side of the factorization channel, the amplitude on the right side, divided by pj square, where j runs from all factorization channels with where for the shifted amplitude, let's say we did this shift of lambda 1 going to lambda 1 plus z lambda 2, and lambda 2 tilde going to lambda 2 tilde minus z lambda 1 tilde. We call this lambda 1 hat and lambda 2 tilde hat. So the only factorization channel with enter here are the ones when 1 is on one side, 2 is on the other side. These momenta are shifted. Then we have these ordered particles up to j, and on the other side from j plus 1 to n, and then 1. And this momentum pj is on shell here. Now it's shifted, so this is also shifted momentum pj hat, so let me call it hat square, and this is 0. And so from this equation we solve for the zj. Yeah. So the pj hat depends on z squared equals 0. That's the equation, and we solve for zj, z we got as zj, and we plug for this shifted kinematics here. And this is what we get from formula. So this is, we can call this the A left, and this is the A right amplitude, which depends on all these legs and on shell P. This is where we ended last time. Any questions about this before we proceed? Okay. So, and here I also said that we sum over factorization channels, but we also sum over the helicity of this particle P. So it can be plus on one side, minus on the other side, or the other way around. Sometimes some of these channels are 0 for some reasons that we will see, that the amplitude is 0 on one side, but in general, all of them are present. Yeah, so we sum over these j, but we also sum over plus minus of the internal particle. Okay, there are no questions to the setup. Let's calculate the first non-trivial amplitude for gluons, which is the amplitude A4, 1 minus 2 minus 3 plus 4 plus, 4-point amplitude. Now, remember, when we use this Cauchy's formula, it was important that the amplitude vanished at infinity. So A and Z was 0 when Z went to infinity. Yeah? Because if there was a pole at infinity, it's some new information at infinity which we need to know to reconstruct the amplitude at the 0 shift. Yeah, the Cauchy's formula would contain that term as a pole. And we don't know what is this pole. Yeah, this is not governed by any factorization properties. Yeah, it's the knowledge of amplitude at infinity. We don't have that a priori knowledge. Yeah. So in order to use the recursions, this must be true. Yeah, for the shift parameter going to infinity, the amplitude must vanish. This is true for Yang-Mills amplitude, but we have to be slightly careful about which momenta we shift. Yeah. So for Yang-Mills, and the same thing will be true for gravity, only certain choices are allowed of the shifts, which is fine. We only need one choice, yeah, and then we just use the correct one. But it's good to know what you can afford and what you cannot. Okay, so normally people, we call one, let's say, IJ shift. This means that we shift lambda I and lambda J tilde. Yeah, so this is an IJ shift. So these labels I and J that we are allowed to shift are correlated with helicities. Okay? So the only thing that we are allowed to do, so there are obviously here 4 options. Either both of them have negative helicity, both of them have positive, or the first one is positive, the other negative, first one negative, the other positive. 4 options for what can happen. So the one which is not allowed is shifting lambda of a negative helicity particle and lambda tilde of a positive helicity particle. Yeah? In that case, the amplitude would not vanish at infinity. It's for something like stupid reason. There is some helicity factor, you are shifting that, and you get artificial growth at infinity. What is allowed is all the other 3 combinations. So plus, plus, minus, minus, and plus, minus. Okay, so this is just one thing to be careful about, what you are allowed and what you are not allowed to shift. And here in all these discussions, I shifted 1 and 2, but there was no reason why to shift 1 and 2. It was just an example. You can shift anything you want. And as I mentioned before, it's convenient to shift adjacent legs, because you don't necessarily have to shift adjacent legs. You can shift 1 and 3 if you want. But if you want to limit the number of factorization channels which appear in the formula, it's convenient to shift adjacent, because then one leg must be on one side of the channel, the other leg on the other side. And then you have fewer terms. So what we will do here is to shift 2 and 3. But again, we can make other choices. One can shift 1 and 2, 3 and 4, or 1 and 4. Yeah. Somehow, the canonical choice is to kind of shift the adjacent ones when the helicity flip, but it doesn't matter. It's just a choice. So we will shift lambda 2 tilde, that is negative, so that one is allowed. Yeah, it's in the allowed list. Going to lambda 2 tilde plus z lambda 3 tilde. Again, calling it lambda 2 tilde hat. And lambda 3 minus z lambda 2, calling it lambda 3 hat. Now, which one is shifted with plus and which one is shifted with minus, it doesn't matter. It's just that the signs must be opposite, such that the momentum is conserved. Yeah, you can redefine plus z as minus z. Yeah, that doesn't matter. Okay. So now the instructions are sum over all factorization channels with 2 on one side and 3 on the other side. So let's see what are all these channels. So there is only one channel. Okay, that's the only thing that we can draw. 2 is here, 3 is here, 4 must be here, 1 must be here, because it's ordered. Now we have to fill also the helicities. So this is minus, this is minus, this is plus, this is plus. This is given to us. And now we have to sum over all here options of what is black and white vertex and what are the helicities of internal. But we have minus minus here, so there is no other option that put plus here and minus here. Okay? Because the minus 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 amplitude is not there in Yang-Mills theory. Yeah? If we consider F-cube theory, some other theory, there it would be there, but not in Yang-Mills. So we got only this option. And this amplitude is a A32, 3-point MHV, k equals 2 amplitude, and this one is A31. So I said in this convention, this is white vertex, this is black vertex. Yeah, just for, just to denote it. Okay? So this diagram gives us a product of amplitude A3, 2, with labels 1 minus, 2 minus, P. Now this is shifted. Plus, and A31 with 3 plus, 4 plus, P minus. Shifted, shifted. And then we have to divide by the P square. Unshifted. Okay, so that's something I didn't emphasize here. That here, the Jacobian, it was this small homework I gave you to figure to do properly this derivation with Jacobians, and you will find that the final Jacobian is 1 over P square. Now this P square is the unshifted one. Yeah. What would happen if this was a shifted P square, evaluated on the factorization channel? It would be 0, because that's the definition of the Z. Yeah. So the thing which this divides is the unshifted one. So in our case, it's S12. Yeah, this is the factorization channel. So this is the term that we have to evaluate. Okay, very good. So now we have to just plug formulas for these amplitudes. So you see that there is this P which shows up. So one way, like kind of the longer way how to do it, is to solve also for these P's. And we can do it, but there is always a trick how to use momentum conservation, because here on this side of the channel, so we can, the P is always P1 plus P2, and this is equal to minus P3 minus P4. So we can always use a trick to get rid of that using momentum conservation. Yeah, it cannot just, because we always can pair lambda p with lambda p tilde, turning it into a momentum, and then is then equal to that. Yeah, if only lambda p or lambda p tilde show up, we have to solve for that. Yeah, so then, but as it turns out, because it only appears on internal line, there is always plus one side, minus from other side, so they always pair into a momentum. Yeah. So let me, yeah, so, but just here to be more instructive, we can actually solve for that, yeah. So, okay, I need to edit things here because these are all shifted. So let's first solve for this shift, yeah. So for z equals, let me call it here z star, because there is only one term, so we will not label it with this index j, there is only one. So the instruction is to build momentum P12. This is headed, which is equal to P1 plus P2 hat. And the square of that is 0. Yeah? So this is equal to lambda 1 tilde plus lambda 2 tilde hat, which is lambda 2 plus z lambda 3. Okay, so this is the headed momentum. This one must be on shell. That's the condition for solving for z. We have to choose the z such that this whole thing is on shell, so it squares to 0. So what it is? So this must be the square of it. Yeah, this is, you can look here, but maybe you can also look here. This is P1 squared, that is 0, plus P2 head squared. This is still 0, yeah, because the headed thing is still on shell. So this is 0, so it's just a dot product, scalar product of these two, yeah, with some factor of 2, but that is irrelevant because we are sending it to 0. Okay? So how is the dot product? We are dotting the lambdas of these two momenta. This is just the angle bracket 1, 2. Sorry. Tildes here. And then the square bracket of lambda 1 and lambda 2 tilde, which is this sum. So it's 1, 2 plus z1, 3. And this must be 0. Okay, so we can solve for z. Yeah, this cannot be 0. That doesn't depend on z, and so this must be 0. Okay, so we solve for z. So the z star is equal to minus 1, 2 over 1, 3. So we found the z star. Okay, by saying that this internal line is on shell. Any questions about that? So now we know, now we have our new momenta, our shifted momenta evaluated on z star. So our shifted momenta So there were a bunch of things which are not shifted, like P1 and P4 were not shifted originally, nothing happens with them. Lambda 2 was not shifted, nothing happens with that. But the lambda 2 tilde was shifted. So the lambda 2 tilde hat was lambda 2 tilde plus z lambda 3 tilde. But this is now this z star. So we plug there lambda 2 tilde plus 1, 2 over 1, 3, lambda 3 tilde. Now we can put this under a common denominator, and there is some simplification which happens. Yeah, it's related to this Schouten identity I showed before. So these two things simplify into lambda 1 tilde times and bracket 2 3 divided by 1 3. Okay, yeah, it's just a simple rule. If you have, yeah, in general, if you have lambda I with tildes or without tildes, it doesn't matter. Jk plus lambda j ik plus lambda k ij, they sum into 0. It's a property just of two-dimensional vector with some plus minus signs. I am very sloppy about the signs here. Well, I put it here with the plus sign. Yeah, it's okay. Yeah, good. So there is a minus sign, but I am generally sloppy about the signs here. Sorry. Yeah. So yeah. Okay. I put the minus sign here, but okay, good. Yeah, there is a minus sign. Yeah, you are right. Yeah. Yeah, I would have to now remember if this thing is with plus sign or minus sign to be exactly correct. This would be with minus. We cycle it. So this is actually with minus if we are precise with signs. Okay, so lambda 2 tilde hat is lambda 1 tilde. Now, why this had to be true? Well, it had to be true because the 1 and 2 hat meet in a white vertex. And we already said that this white vertex in this 3-point amplitude, the lambda tildes are proportional. So this was actually, we were forced into it, even if we didn't have to calculate it. We could directly write the result, but we got it also as a result here. This was mandatory. Yeah, it was not optional. And we can do the same thing with lambda 3. So the lambda 3 hat is lambda 3 minus z star lambda 2. So this is lambda 3 plus 1, 2 over 1, 3 lambda 2. We can also write it as 1, 3 lambda 3 plus 1, 2 lambda 2 divided by 1, 3. And now you realize that this lambda 3 and lambda 3 tilde together form a momentum P3. And the same thing, this is a momentum P2. Yeah? So the result can be also written as momentum P2 plus momentum P3. Now, not with the space-time index, but with this AA dot index in this matrix form, which is dotted with lambda 1 tilde, and this is divided by 1, 3. But we can also use momentum conservation, and instead of P2 plus P3, write P1 plus P4 with a minus sign. Yeah? So this is also equal to minus P1 minus P4. So if we plug it here, P1 dot lambda 1 tilde is 0. We are dotting the same lambda tilde spinors. So the only thing which survives is the P4. So now if we dot it with 1, we get the square bracket 1, 4, and we get lambda 4, and 1, 4 divided by 1, 3. Again, we had to get this because 3 hat and 4 meet in a black vertex. And in the black vertex, all the lambdas are proportional. So this lambda has to be proportional to this lambda. Yeah. And we also got it by explicit calculation. So having calculated that, we can also now calculate the internal momentum P hat. So basically, the p hat is already fixed by these conditions from this vertex and that vertex, because p meets with 1 and 2 in the white vertex. So it must carry the lambda 1 tilde from here. But it also meets in this vertex with 3 and 4. So it must also have the lambda 4. Yeah, so the only thing is what is actually the prefactor. But the spinor part must be lambda 1 tilde, lambda 4. There is no other option. Yeah. But we can also, without realizing it, just solve for that. So the p hat is p1 plus p2 hat modulo the sign. Yeah, so depending if the p flows here or here. These signs are never important in the calculation. At most, they just change the overall sign of the amplitude. So I can just let the p. So sorry, in the way how I wrote it was p was pointing here. Okay, so just to be slightly precise, like we can put minus sign here. So this is minus lambda 1 tilde from p1, and p2 hat is lambda 2, and lambda 2 tilde hat was this, lambda 1 tilde 2 3 over 1 3. Okay, so the lambda 1 tilde factors out, and we get lambda 1 plus lambda 2 3 over 1 3. And there is some minus sign overall. So we again put it under the common denominator, lambda 1 1 3 plus lambda 2 2 3 over 1 3. And we again realize that lambda 1 and lambda 1 tilde is p1, and this is p2. So we can also write it as p1 plus p2 acting on 3 divided by 1 3. Okay, but p1 plus p2 is minus p3 minus p4. So the 3 again vanishes if we dot it with lambda 3 tilde, so only the 4 survives. So now considering the minus sign and the antisymmetry, we get lambda 1 tilde, lambda 4, 3 4 over 1 3. Okay, which exactly matches our intuition that p must share the lambda tilde spinor of 1 and lambda spinor of 4. We also got it here by explicit calculation. Okay, so we solved for all these shifted momenta. Yeah, they are solved now for. Any questions here? Yeah. So, but no, okay. Yeah, well, lambda, okay. So maybe it was an overall, maybe I didn't do this identity correctly with signs. Maybe it's an overall positive sign. Let me think, yeah. Lambda 2, so maybe there is a positive sign here. Yeah. Okay, thank you. Yeah. I'm being sloppy, as I said, I'm being sloppy with the sign. If you do the signs correctly, you will never face these problems, yeah. Okay, good. So, so we solved for the lambda 2 tilde, lambda 3. We solved for the p. Now, you can ask one question, because once we write in the formulas for these 3-point amplitudes, we need lambda p and lambda p tilde to factor there, to enter there. But we got p as a momentum. Now we have to divide it into lambda p and lambda p tilde. So now you might think there is a slight problem, yeah? Because we have these spinors. Does this factor belong to lambda or lambda tilde of p? Now, you can do it however you want, because we know that the division into lambda and lambda tilde is not unique, because you can multiply by this t factor and divide it, and it should be the same thing. Yeah? So you can do it however you want, and you always get the same result. This is another way how to say that the result for this product will only depend on the momentum p itself, the p hat, not separately on the lambda and p and lambda p tilde. Yeah. But once we do when we do the calculation, we have to divide it somehow. It doesn't matter how, and the result will be the same. Has to be the same. All right. So we make some choice. Let's say that this factor will belong to, let's say, belongs to lambda. Yeah. So we call this lambda p tilde hat, and we call this lambda p hat. Okay, so now let's evaluate the 3-point amplitudes. So we have the 3-point amplitude 1 hat minus, 2 minus, p hat plus. This amplitude is given by 1 hat 2 cube divided by 2 p hat 1 p hat. Sorry, not 1 hat. Sorry, what I'm doing here. Sorry, nobody noticed I headed the wrong label. This should be headed. This should be headed. We did the 2 free shift, yeah. So this is headed. This is, okay, things are headed correctly now. Okay, however, the 2 hat for lambda is just lambda 2, because that was not shifted, yeah. Lambda 2 hat is just lambda 2, because we shifted lambda 2 tilde, not the lambda 2 itself. Okay, and the lambda p hat, as we calculated over there, was lambda 4, and then 3, 4 over 1, 3. So we just plug here in this formula for that. So this is just equal to 1, 2 cube divided by 2, 4, 3, 4 divided by 1, 3. And then 1 p hat is 1, 4 divided by, multiply by 3, 4, 1, 3. Okay. So far we leave it in this form. I will then show that just momentarily that exactly because of 4-point kinematics, we can simplify dramatically and rewrite the whole thing. Yeah, but this is what we got from this first factor. Any questions about this? Yeah, we just plugged for the spinors that we calculated. How is the lambda 2 has to be equal to lambda? Okay, because we didn't shift lambda 2. It's a question from the Zoom. We shifted lambda 2 tilde and lambda 3. So lambda 2 was not shifted. So that's therefore it's equal to lambda 2 hat is lambda 2, and lambda 3 tilde hat is equal to lambda 3 tilde. Okay, so now let's do the other amplitude, A31 of 3 plus hat, 4 plus, p minus hat. So this is equal to 3 hat 4 cube divided by 3 hat p hat and 4 p hat. Okay, so again, note that lambda 3 tilde hat is lambda 3 tilde, and lambda p tilde hat is lambda 1 tilde. It was the result of our calculation. Okay, so we plug it here. We got 3, 4 cube divided by 1, 3, or 3, 1 up to a sign, and 4 p hat is 1, 4. Okay? I leave this board here and continue here. So now we have to put everything together. So we just take a product of these two 3-point amplitudes. So this is 1, 2 cube, 1, 3 square. And the other thing we had in the numerator is 3, 4 cube. Then we had 2, 4, 1, 4, 3, 4 square. And from the other factor, we had 1, 3, 1, 4, 1, 3, 1, 4. And then we have to also divide it by S12. So S12 is the same thing as S34. I write it in this form as 3, 4, 3, 4. So we put here 3, 4, 3, 4. Okay, and questions, how we got to this stage. So now we cancel some stuff. So there is 3, 4 square and 3, 4 and 3, 4 cube. I cancel. 1, 3 here cancels the second power here. So far we are getting 1, 2 cube, 1, 3, divided by 2, 4, 1, 4, 3, 4, and 1, 4. Square bracket. This is still not exactly yet what we want, but we will use a kinematic relation. So now the product of 2, 4 and 1, 4 can be rewritten. So let me put the 2 to the 4, the 4s kind of together. This is up to a minus sign here. So this 4 is a P4. Again, the P4 dotted with lambda 2 on one side, lambda 1 tilde on the other side. So this is P4. And the P4 can be written as minus P1 minus P2 minus P3 using momentum conservation. Now if we, so I can write it as this mixed bracket 2, 1 plus 2 plus 3 and dot it with lambda 1 tilde on the other side. However, dotting 1 with lambda 1 tilde is 0, dotting 2 with lambda 2 is 0, so the only thing that survives is 3. So this will be equal to 2, 3, 1, 3. Now this thing with the minus sign, but we are being sloppy, or I'm being sloppy with minus signs all the way. So important, okay, I'm sloppy with minus signs, but in a particular way. I'm only sloppy with overall minus sign. Yeah. In case we will have two terms contributing, the relative minus sign between them or plus sign is important. But the overall sign, if we get an amplitude or minus an amplitude, is irrelevant here. Yeah. Okay, so plugging for this, so instead of this term and this term, we get 2 free and 1 free. So this 1 free cancels the 1 free in the numerator, and we get a final formula. 2 free, 3 4, 4 1. Actually, here I can put the minus sign here, and it flips when we flip 1 and 4 to 4 1. So here actually we got the right sign in the end. So this is a 4-point amplitude. You can see that it has exactly the same structure as this Park-Taylor factor. Yeah, and this is something which will generalize immediately to any n-point amplitude. Any questions here? How we got this 4-point amplitude? Yes, so we are now, so we did it for 4-point. We are now ready to prove the form of the Park-Taylor factor by induction. So we already know that A3, 1 minus, 2 minus, 3 plus has this form. 3, 1. 4-point amplitude that we just proved has this form. So we now assume that the n-point amplitude, or n minus 1 point, has of 1 minus, 2 minus, and the rest are pluses, has the following form, and then we will show that the same thing then applies to n-point. Okay, is it clear what we want to do? So we will use the same 2-3 shift. So we, in the formula for n-point amplitude, we again have only one term. Yeah, because so we have 2 minus, 3 plus, these are shifted. There is 1 minus. This goes all the way down to n plus. Because there is minus minus, we have to add plus here and here minus. So this is a complete analog of the term that we had over there. Okay, you might think, are there more terms? Yeah, can I put some of the legs from here, here? Yeah, so let's just see. Are there any terms like that? So if I move, let's say this doesn't go all the way up to n, but only up to some j. And then the rest of the legs are on this side of that channel. Now, what is the problem with that? How do I fill the internal helicities of P? The problem is that all these guys are positive. So the best I can do is to put here minus sign and here plus sign. But still, this amplitude has only one minus sign. So it's the one where we said is 0. Yeah. So this one is still 0. You cannot do anything with that. So this is 0. Okay. Yeah. So this is the only term that we have. Yeah. Which was also here true for 4 point, but it is true also for n point. There is only one term in the recursion. Okay, so that's our one term in the recursion. So we just evaluate this term. So we should solve for z equals z star. But you can see it will be the very same formula. Yeah, because it would be the P1 plus P2 hat square must be equal to 0. So we get, yeah. This one, sorry. Where are you? Sorry. You are right. Yeah, I wrote the wrong diagram. Yeah, very good. Thanks for noticing. The one which is not 0 is actually putting all the ones here on this side. Yeah, good. Thank you for noticing. That one was also 0. Yeah, the one which is not 0 is this one. Good. Yeah. So if I have, so this amplitude is 0, unless this is a 3-point amplitude. Yeah. And this is non-zero. This is our n-1 point MHV amplitude. So the only diagram that we have is the one which has only 2 legs on this side, and the rest of the legs are here. Because these guys are protected. They have 2 minuses already. This one has only 1 minus, so the only non-zero is for 3 point. Okay. Yeah, sorry. I was... So the condition is actually P3 plus P3 hat plus P4 square is 0. This was the same condition we had there, because in that case, this was equal to P1 plus P2 hat. Yeah, here it's important to take this version, because this is now not equal to the sum of these two momenta. It's equal to the sum of these all momenta. Yeah, so this condition boils down to P3 hat dot P4 is 0. So from that, we can solve for the Z star. So here we cannot use all these tricks about 4-point kinematics. This is not a 4-point kinematics anymore. So we will always get just one formula with not such these relations. So here, if we look at it more closely, in P3 the lambda was shifted, not the lambda tilde. So the lambda tilde part just factorizes as 3,4. And the thing which will be shifted here is the 3,4 minus Z24. Yeah, the lambda 3 tilde shifted. It was already like one blackboard ago on that side. Was lambda 3 minus Z lambda 2. And this is 0. So here from that we solve for Z. Yeah. So the Z is equal to 3,4 over 2,4. It's actually the same that we got for Z before, but before we wrote it in terms of square brackets, which were equivalent to this one because of 4-point kinematics. Now it's not equivalent. So now we get just this representation using these angle brackets. Okay, and then the amplitude will then be equal to the product of these terms on the factorization channel. So it's an n-1 point amplitude, MHV, for 1 minus 2 minus hat P plus hat, and then we have 5 plus up to n plus, and the MHV bar amplitude A31 with 3 shifted, 3 plus, 4 plus, P minus shifted. And now it's divided by unshifted unshifted P square, which is S34. Yeah. You can also write it in terms of S of this multi-particle on the other side, but because of momentum conservation, it's just S34. Okay. Now now we will be here a little faster. So instead of solving for this P, I use this general formula using this small trick with the momentum conservation. So this first formula is just equal to in this step we assume that the n-1 point amplitude takes this form. So I just plug for that. This is 1, 2 cube, 2p, p5, 5, 6, up to n1. Then is 1 over 3, 4, 3, 4. And then it's multiplied by the 3-point amplitude of that. And this is 3, 4 cube. I am already removing these hats. Yeah, I'm removing these hats because we knew that these hats had no effect in these amplitudes because lambda 2 was not shifted, and this only depends on lambda 2. Here, lambda 3 tilde was not shifted, and this only depends on lambda 3 tilde. Yeah, that's why we use this convenient shift to just run it as quickly as possible. So, and this has in the denominator 3p and 4p. Yeah, the only non-trivial part here is the p. But here we can use the trick because the p shows up twice in the denominator here in the angle bracket and twice here in the square bracket. So I combine them in the same way as we did before into momenta. I write 2p and p4, this product, and this is the momentum p. And we can write it as, yeah, so okay, here is a slightly subtle thing, but okay, or not subtle, but I will do it in one step instead of two. So the P is P3 hat plus P4, okay? The P4 gets killed by this 4. Yeah, so the only thing which survives is the P3 hat. The P3 hat has the unshifted piece, which is just P3, and the shifted piece. The shifted piece depends on lambda 2, and that gets killed by this 2. Yeah, so the only thing that survives is actually 3. Yeah. So this is equal to 2, 3, 3, 4. Okay? And similarly, the 5p we combine with p3. And here the only thing which survives is 4 from p. So this will be equal to 4, 5, 3, 4. Okay? So if you do it long way, you have to solve for p, and you just plug into this formula. Yeah? I am doing it a little bit faster because I know exactly how the p looks like. It's a sum of these two momenta plus the piece which is shift, but the shifted piece depends on lambda 2 and lambda 3 tilde. And in these combinations, it's exactly annihilated by the stuff that we dot it with. Okay, so we are done here. We just combine everything together. So, okay, I can do it here so that you can see it. We want to kill this 3, 4 cube. So 1 power is killed by this, 2nd power is killed by this, 3rd power is killed by this. This is gone. Okay? And the thing that we were missing, and we got here is 2, 3, 3, 4, 4, 5. And then we continue the sequence from here. Yeah, so okay, I'll just write it here. So then what we got was 1, 2 cube. We don't get 1, 2 in the denominator, but we start with 2, 3, 3, 4, up to n1. Any questions about that, or was it too fast, the last step? Yeah. Now, just a small comment about this MHV. This MHV formula is particularly simple because we can also choose just arbitrary helicities. Here, everything that we chose was 1 and 2 being minus next to each other. But suppose that you have 1 minus, then bunch of pluses, and then you had some j minus, and then the rest are pluses. So you can already see from this formula that we had that we could also just put 1, 2 to the 4 in the numerator and add 1, 2. And this thing in the denominator would be then completely cyclic. Nothing would be missing. So this is exactly what happens. This 1, 2 to the 4 is so-called helicity factor. And that was the thing which was responsible or came from the fact that 1, 2 were the negative helicity. If you have something else negative helicity, then the equivalent factor will go into the numerator. So here the factor will be 1j to the 4 divided by this sequence, 1, 2, 2, 3, up to n1, without any kind of holes in the in that. Yeah, and you can also prove it using these BCFW. Yeah. Okay, any questions here? Yes.
Can you repeat his question?
If I understood, is there a factorization diagram? Then 5 is here. Now that was the argument here. There is no, yeah, because once you have 2 on one side, you need to have 1 on that side as well. So the 2 minuses are on one side, and none of the minuses are on the other side. You cannot exchange 4 and 5. It's ordered. It goes with this ordering, 3, 4, 5. So therefore, that's the strength of the ordering. It just doesn't allow all these other orderings. So there is only one term. If we calculate this thing with like the minuses being this like far from each other, we will have more terms that contribute. Yeah, this will be not the only diagram allowed. Yeah, you can just check it for yourself. Yeah, they will still sum into this formula, but yeah, there will be multiple terms which contribute. Yeah, so I think yes, more question. Yeah. Yes. Now here there was no, the hat was the same as unheaded because we didn't shift lambda 3 tilde. We shifted lambda 3. Yeah, so that was the reason why we did these convenient choices to what we shift. Yeah, we could do also inconvenient choices. We get more terms which contribute, and we have to work a little harder. It's possible. It always works in the end. Yeah, it's just that I kind of secretly made some good choices to make it smooth for calculation. But if you don't do good choices, you make bad choices. You still get the right result after more work. Yeah. How is the lambda 2 to be? Okay, maybe that was the question from before, right? That's not a new question. Okay. Okay, so let me now schematically show how the calculation would work for beyond MHV for other helicities. And then I wanted to do the gravity amplitude here as well. And that, but it would be fast. And then maybe just 1 minute of some comments about where it all goes. So, so this now works for any helicity. We just did it for this simplest one with 2 minuses for the MHV. But the first real new case is a 6-point amplitude, which we would call NMHV, where the number of minus helicities is 3. So now the convenient shift to do would be shifting 3 and 4. Yeah, this minimizes the number of terms. So it would be shifting lambda 3 tilde and lambda 4. Yeah, 3 is minus, so we have to shift tilde, and 4 is plus, so we shift the lambda. So this is the one which behaves correctly at infinity. So the term which would contribute are following. So 3 is minus, 4 is plus on the other. So we can just put one more plus here. Then the internal must be minus. This one will be plus, and we fill the rest on the other side. So 6 plus, 1 minus, 2 minus. So that one is definitely allowed. This has 3 minuses, 2 pluses. This is non-zero. This one is 3-point with 2 pluses. That one is non-zero. That one is fine. We can do yeah, but as we know, we cannot put 6 plus here on that side. Now, once we put 6 plus here, it's a 4-point amplitude with 1 minus, and that one is 0. Same argument as before. Yeah? So we cannot put 6 plus here. But we can put 6 plus and 1 minus to add 1 more minus to this side and choose minus here. So that one is allowed. Okay? 2 minuses, 1 plus, that one is fine. 2 minuses, 3 pluses, that one is fine. Okay, so these are the only 2 non-zero terms that we will have. But we have 2 of them now. So I will not do the calculation here, because that would take a bit longer. But in principle, it's exactly the same that we had before. But the result is a sum of 2 terms. Yeah, there is no way around it here. Yeah. There doesn't exist any even smarter choice when it would be a single term. Yeah, it's just 2 terms. So let me show how the terms look like. Yeah. Once you calculate it, so calculate the homework. And it is also related to what I said about the spurious poles. So the first term has this mixed bracket. This is P4 plus P5 in the numerator. It has some poles. Now it has a multi-particle factorization pole, S345, something which didn't show up in the MHV amplitude. It has this type of brackets. It has this type of brackets. Know that all these poles are physical poles. They would show up in Feynman diagrams as well. This is the multi-particle pole. This is S34, just 1/2 of it. This is S45, S61, S12. Yeah, but just half of it. Yeah, just either the angle or square brackets. But there will be also a term which is not P square. It came from P square for shifted momenta. But once you evaluate it for Z star, it became something which doesn't look like p square. And the other term will look like this. Okay, you see that the same factor here shows up in the denominator. And indeed, if you put these guys together, this pole cancels. Yeah? However, you get some more messy expression. Yeah? These are kind of very compact, with very simple numerators. If you put it together and try to cancel that pole, you get some longer expression. So it's not a good idea to cancel it. Yeah, it's efficient to leave it in, and that's what the recursion gives you. Yeah, add the spurious pole, and you get simple expression. Yeah? But if you calculate the residue, let's say, of this on this pole and residue of that on the same pole, they cancel each other. And they must, yeah, because this is not a physical pole. Yeah? So this is unphysical pole. This is something which would never happen in Feynman diagrams. You will never have such a pole, because there all poles are 1 over p squared. Yeah, not here. Now this expression, as the Park-Taylor formula, if you want to get it from Feynman diagrams, you have to take these 220 Feynman diagrams that Park-Taylor had, put the helicities there. You put one helicities, you get Park-Taylor formula, this MHP formula. You put there these helicities in the polarization vectors. You get an equivalent of that formula after this pole is cancelled. Yeah. But you can see that it's not. Yeah. You can still write it on one line if you write it smaller font. Yeah. But the appearance of these spurious poles is a general feature of recursion relations. Okay, any questions here? Yeah, I didn't derive these formula. I just said it would come from that. Yeah. We do have this diagram. Well, that's because of the shift. You need 3 on one side and 4 on the other side. Yeah, because that one will not show up in the recursion. Yeah, you need the shifted legs being on different sides of the channel. Yeah. So I want to get to this 4-point graviton amplitude, which will be quick. But let me then make here one comment, because I already made a big deal of this spurious pole. And so this is really saying extremely quickly a very long line of research and thoughts. But around 2009, Andrew Hodges, who's a mathematician, or was a mathematician in Oxford, he studied these recursion relations. So people used already by that time. They were formulated in 2005. Yeah, around 2008, people already used them, 2009, to just calculate amplitudes for higher multiplicities, 10-point, 12-point, yeah, different helicities. But he was really bothered by understanding why these spurious poles cancel. Yeah, we know from first principles they must cancel because the recursions reproduce the right amplitude. But he was bothered, like, how do they kinematically cancel? How do I see they cancel? And it's very hard to see it in momentum space because, as I said, the only way how to see it is basically put these two expressions under common denominator, get some gigantic polynomial in the numerator, and just use a lot of identities and momentum conservation and try to generate this pole and cancel it explicitly. But that's not very insightful. Yeah. So he used different set of variables, not momentum variables or spinor helicity variables, but so-called twister variables, or in his version, momentum twister variables. As kind of, as the right variables to expose these cancellations. So he took these two formulas, literally these two formulas, and rewrote them in terms of momentum twisters. Yeah. And now it will not tell you much, the explicit formulas, but I will just flash them here. They contained not 2 brackets as these, but some 4 brackets. Yeah. So these labels in the 4 brackets again corresponds to particle labels. So But it's literally just change of variables. Yeah, there isn't much physics at the moment in it. So he just changed the variables, and all the so this was one formula, and there was also a similar formula for 1, 2, 3, 4, 5. Yeah, there was one more formula. But the important thing is that there was this term 1, 2, 3, 5, which was just this pole written in terms of these new variables. All the other terms corresponded to these other physical poles. Yeah, there is something in addition to it. You have to kind of factor out the Park-Taylor factor, which factors out of the whole thing, and so on. So there is more story. But the important part was understanding how this thing cancels, how this spurious pole here and here cancels. And then he realized that these expressions that he got for these individual terms corresponds to volumes of tetrahedra in the twistor space. The same formula are reproduced by the volume formula of creating the tetrahedron in this twistor space. When the kinematical data come from the position of these vertices, they are labeled by these twistor variables. You build that from these vertices, you calculate a volume, and you get the same formulas. And now there is a small step. Now you have to take two of these tetrahedra, because you have two terms in the amplitude from these recursion relations. So if you sum two of them, you get one big tetrahedron, and you basically chop out a smaller tetrahedron. And the amplitude corresponds to a volume of this polyhedron. And this piece, which canceled, this is a vertex that cancels in case you take the big one and subtract the small one, was this spurious pole, which made completely manifest that the amplitude corresponding to this volume doesn't have this as a vertex, where the vertices of this object corresponds to the poles in the amplitude. So this was the early indication that there is a relation between amplitudes for gluons and volumes of some geometric objects. And this eventually, when you generalize it, you have to then consider not just tetrahedra, but some more complicated abstract mathematical objects, and that led eventually to the amplituhedron that we did with NEMA several years afterwards. Okay, so that's the story about gluon amplitudes. Now I know that I'm plus 4 minutes, but I wanted to do the gravity for my amplitude, so let me just quickly do it, because it's basically the similar calculation that we did before. So I just write how to do it and write the result, but it is the same that we did for gluons, for 1 minus 2 minus 3 plus 4 plus. Remember, we had for the 2 free shift, we had this diagram. So it's exactly the same diagram for gravitons. The only thing that these 3-point amplitudes are graviton amplitudes. So they are squares of the gluon amplitudes. Yeah, so this then starts as 1, 2 cube over 1p, 2p, square 1 over S1, 2, and then 3, 4 cube, 3p, 4p square. Yeah, we had this formula without squares for the gluons. We got the Park-Taylor formula for 4-point. Now we just square these things that are coming. Otherwise, everything is the same. Just the 3-point amplitudes are squares. So once you do it, you get a following expression. You get 1, 2 to the 8 in the numerator. Then you get 1, 2, 2, 3. Yeah, an important thing here. So sorry. So that's something I didn't say. So important. No, okay, sorry. So here you get just one expression. Yeah. you don't have only these poles that we had before, but you have all poles, because there is no cyclic ordering for gravitons. There is no cyclic ordering, so you get all poles. You get also 1, 3, and 2, 4, which were not present. And if you do the calculation one way, you also get a square bracket 2, 3 in the numerator, and let's say, and you get a square of this bracket 1, 4 in the denominator. So I write the formula again. This is just a straight result of the recursion relations without kind of doing any more work. So, yeah. The gravity amplitude doesn't have cyclic ordering, so the poles that in the denominator, you get all of them. But there was a puzzle for some time, because you get a square of the pole here, which seems bad, because that seems to naively violate the simple poles in the amplitude, which comes from Feynman diagrams. However, it's an early indication that for gravity amplitude, it's like very important to understand momentum conservation. Because this factor 2, 3 over 1, 4, and 1, 4 was the thing which squared the pole, is permutational invariant. That small exercise that you can do, that this is also equal to, for example, 3, 4 over 1, 2. And this is also equal to 1, 2 over 3, 4, and all other combinations. So the amplitude is completely up to this helicity factor. The rest of the amplitude is completely permutational invariant in all labels. However, if you want to write an explicit formula using spinor helicity variables, but any variables, no variables are known that you can use to expose the permutational invariance. Yeah? Because you write it like that, and now it doesn't look permutational invariant. There is 2, 3 in numerator and 1, 4 square in the denominator. It seems to break the fact that you can permute the labels and you get the same thing. But there is an obstruction to write it explicitly, but it is permutational invariant, because you can write this factor in many different ways and write many different formulas which are all equivalent. Okay, so I just want to say that, and this is basically, from that point of view, kind of an unsolved problem, how to write gravity amplitudes such that the kinematical formulas respect the symmetries of the amplitude. The Park-Taylor factor nicely exhibited the cyclic symmetry of the amplitude. Yeah, you had all these chain 1, 2, 2, 3, 3, 4 up to N1. You can cycle it, you get the same thing. You just cycle it around. But for gravity amplitude, it's a different story. Yeah, there is not cyclic symmetry. There is even stronger permutational symmetry, but you cannot make it manifest in any kinematical formula. So are there any variables which make it manifest? That is unclear. Not known. But the problem is even for the simplest 4-point amplitude. The only amplitude which manifests this symmetry is the 3-point amplitude. Yeah. But starting 4-point, you have to rely on this type of relations to show that there is a permutational symmetry. Okay, I stop here.
Okay, let's thank Jaros. Questions?
Well, I do like to know if you have calculated cross sections with these amplitudes. It's a simple question, not expert question, but you evaluate the scatter amplitudes in quantum field.
Yes.
For the final goal, it is cross sections.
Yeah. Not me personally, but yeah, people use these amplitudes and enter it for the cross sections. Yeah, especially with these gluon amplitudes at doing LO and NLO calculations for QC. Yeah, cross sections. Yeah, with gluons, like in order to make it actually useful for, let's say, LHC calculations and QCD background, you have to do a little more work because these are gluon amplitudes. You have to then add some Parton distribution functions and some non-perturbative QCD physics to turn it into an hadronic scattering. Yeah. So this is not part of this study, but we have the result of that is the first part: gluon amplitudes in perturbative QCD. Then there is an extra work that must be done for hadrons, and then you calculate cross sections. But yeah, so people did it. Of course, people did it, but kind of our task is just the first problem. But yeah, I can confirm, Zvi could talk more about it if he was here, that these results were used to calculate cross sections. Yeah. Of course, with cross sections, it's much harder to get analytic formulas, so most of it is done numerically. But there are some complicated phase space integrals for these higher point scattering. But the formula were used for that.
Sorry,
Yeah.
could you perhaps just talk a little bit about the geometric interpretation of the unphysical poles that you talked there?
Okay, well, that's a very long story. Yeah, so I just try to do a very just a very side comment of what is the significance of these spurious poles. Yeah. So here I just wanted to say that the BCFW recursion give you one representation of the amplitude, but it seems perfect in a sense that it gives extremely compact formulas, yeah, very simple formulas. But it has this one thing about the presence of spurious poles. So it was a puzzle to understand what is their meaning and how do they cancel. And the understanding which evolved was this geometric formulation, basically saying that the amplitude is a one object. That is also, this was more like a philosophical question. You have the amplitude as a sum of Feynman diagrams. You have the amplitude as a sum of terms in the recursion relations. Is the amplitude one object, or should you always think about it as a sum of some elements? So, and in this formulation, amplitude is a one object. The one object is some geometry. It's a volume of some geometry. Now, you can break it into pieces. You can triangulate the geometry. One triangulation gives the BCFW recursion relations. Another triangulation gives Feynman diagrams. Yeah, and for the triangulation that gives BCFW breaks the object into two pieces. The triangulation that gives Feynman diagrams breaks the same object into 220 pieces. It's not the most efficient, but it's possible. Yeah, it's a valid triangulation. It's just complicated. Yeah, but and any spurious poles that you get in BCFW corresponds to points that you use to triangulate the object in terms of simpler things. Yeah, so the Feynman diagrams is a triangulation which doesn't use any extra points. Therefore, you don't have any spurious poles. Yeah, but
all right, thanks.
Yeah. Yeah, graviton.
For graviton amplitudes, when you write the BCFW recursion and you break it into all of these channels, are the channels still are the channels still ordered, or?
No, they are not ordered.
Okay.
You have to sum over all ordering. 4-point, the situation is special because you have only, apart from the shifted guys, you have only one more minus and one more plus. So there is no no sum over permutations to be made. But if you already considered slightly more complicated amplitude, you would have to sum over things. Like here was the question about the Park-Taylor factor. Can we swap 4 and 5? You cannot for gluons, but you can for gravitons. Yeah, you can swap it. You have to sum over all of them.
And one other small notational question. What does the 6R stand for on the amplitude?
GR.
Oh, that's GR.
GR, sorry. Okay. It's not 6, GR. Yeah. Yeah. So the problem with gravitons is that there is no ordering. They are not colored, as we showed before. For 4-point, the gravitons are not colored, so they are naturally. You cannot break the graviton amplitude into a sum of simpler amplitudes. There is nothing like that. You have to consider everything at once. Yeah.
Yeah. So you said that amplitude corresponds to a tetrahedron, and looking at Feynman diagrams corresponds to a triangulation, and recursion relation the others. So Feynman diagrams are not gauge invariant by themselves.
Yes.
While in the recursion relations, everything is gauge invariant, right? Is there interpretation of that in terms of these triangulations?
Right. So there is a subtle interpretation of the non-gauge invariance. So in effect, if when we triangulate this object, we did not use any new faces. We only, this this point was given by phases which were already in the problem. The Feynman diagrams would start to slash it with some arbitrary phases, which exactly correspond to like the arbitrary choice of a gauge, yeah, the non-gauge invariants, yeah. It's a very slightly subtle point, but it's an extremely good question, yeah.
I think we have some questions.
And there is a question.
Yeah, 3 questions, I think.
Okay, there are codes. So there is a nice code by Mathematica codes. Yeah, these are Mathematica codes by Jacob Bourjaily, my collaborator, who implemented the BCFW in the momentum twistor space. Very efficient code. Yeah, you can calculate 16-point amplitudes for gluons if you want for different helicities. There is a different code by Lance Dixon and Johannes Hahn, which also calculates quarks. Quark amplitudes, because one thing I didn't discuss here, this was all about gluons. You can embed it into supersymmetric theories, and it's convenient to embed it in n=4 supersymmetric Young-Mills. It's maximally supersymmetric Young-Mills. Then the calculation of these superamplitudes is at the same order as the calculation of these gluon amplitudes. However, you also have amplitudes for all these other particles in the n=4 supermultiplet. The n=4 supermultiplet also contains quarks, fermions, but they are kind of in the wrong representation. They are in adjoint rather than fundamental, where the quarks are in QCD. But for 3-level amplitudes, there is a trick how to get fundamental from adjoint. So Lance Dixon and Johannes Hahn wrote a code how to calculate also amplitudes for quarks and gluons. Yeah, they are also in Mathematica, the code. So yeah, so there are available codes. There are probably also some unpublished codes for people who want to, Mathematica is great. I like Mathematica. You can do anything there, but there are probably more efficient implementation in Python or I don't know, somewhere else. But these are probably not public, yeah. But if you want to just to play with amplitudes, this code by Jacob Bourjaily and Johannes and then Lance Dixon are perfectly fine to generate a lot of amplitudes, yeah.
I think we also have questions on twistors. These are interesting.
Twistor space is valid for loop amplitudes. Okay, it's a good question. Yes, but then not for pure gluons. It's the formulation for loop amplitudes, in particular for the loop integrand. So that's something that Zvi also mentioned in his talk. There is a loop integrand. It's a rational function that you are supposed to integrate to get a loop amplitude. But the loop integration is a complicated procedure. There are divergences that you have to regulate. You get some complicated transcendental functions, which is not understood. Yeah, there is a lot of unknown things. But the loop integrand, if you think it's a sum of Feynman diagrams before you integrate, it's a rational function, depends on loop momenta, in addition to external momenta. So this function has a geometric interpretation for n=4 super Young-Mills theory. Yeah, so for this special theory in planar limit, so in that case, the particles are still ordered. We take the leading single trace approximation, the large n. And in that case, the same story which applies for 3-level amplitudes for gluons also applies for all loop integrand, when enough loops. Yeah. But not for pure gluons, yeah, for this n=4 super Young-Mills. At 3 level, there is no difference between gluon amplitudes in pure Young-Mills and in n=4 super Young-Mills. But at loops, there is a big difference, yeah. n=4 is much simpler theory. It's UV finite. It's a finite radius of convergence. You don't have any renormalization. And it's a great toy model for gauge theories, but it doesn't have any confinement. And, yeah. But at the same time, people have played with this theory for a long time because it's the theory which shows up in ADS-CFT correspondence as well as the low energy expansion of the string theory.
There is one question also for twistors for gravity amplitudes.
Twistors for gravity amplitudes. Well, there have been a lot of attempts to do it, but the problem is it comes back to the cyclic ordering. The twistors naturally in this formulation are cyclically ordered. The gluon amplitudes are cyclically ordered, so they were the great place to use them, but the gravity amplitudes don't have cyclic ordering. And so it's not clear how to define the variables which will not rely on cyclic ordering. Yeah.
Any further questions? Okay, so let's thank Jaros.